This is the second part of lecture 4, which is related with unit operation modeling and process design. In these sections, we are looking at how to model unit operation and then how to simulate the overall process in an integrated manner. So we are not just looking at one single unit operation. We want to look at how we can integrate overall process and how to see the performance of the overall process in the context of chemical process design. This is a very simplified flow sheet for chemical process. So feed A is used for the production of the B. Then the reactor is involved inside the chemical process. Then we might need to introduce heater in order to increase the temperature of the feed. So the feed is increased, the temperature of the feed is increased before being fed to the reactor. Then after reactor, maybe the reaction is done in a exothermic environment. So a lot of the heat might be generated. Then the temperature is increased from the reaction. Then the cooler is introduced to reduce the temperature, or we may need to recover the heat through the cooler in order to produce steam. For the separator, may be required at a low temperature compared to reactor. Then we needed to introduce cooler. So the heater and the cooler are another name of the heat exchanger. Okay. When we're using the steam, for example, in order to provide the heat to the process, we typically call that heat exchanger as a heater. Then for the cooler, the heat exchanger is involved in providing the cooling source. In other words, taking out the heat from the process. Then we typically call that heat exchanger as a cooler. It looks like the separator involved in this diagram is a column. So you may think this is the distillation column. This may be absorption column. So there are different types of the separators involved in the chemical process. Then the task of the separator is to separate the product against the undesired product or byproduct or the waste. So here the product B is recovered from the separator. Then the unused the feed material A is recycled back to the feed. So it looks like the recycled component A is gas phase. So the compressor may be required to recover the pressure drop throughout the unit operation before the separator. So heater and the reactor and the cooler and the separator, and also these are connected with the piping. So there might be some pressure drop. So in order to recover the pressure back to the pressure we want for the reactor, then we might need to introduce compressor. So it looks like this recycle stream is gas phase. However, the separator produced the product is liquid phase. Now we needed to pump to transfer the product of the B probably somewhere in the storage tank or downstream process. Okay, so it looks like the product B is produced from the liquid phase. So if we can avoid the gas phase the transportation, it is desired because the compression is expensive rather than pumping. So typically in the separator, we try to produce the product at the liquid phase rather than the gas phase. But some case we may not be able to avoid the gas phase production. Then we have to install the compression when the pressure should be increased. Okay, so the unconverted material A recycled back and combined with the feed A, then reheated through the heater, then used in the feed in the reactor. Of course, we have the very simplified reaction mechanism given for this reactor as an illustration purpose, but this is very simplified reactions. You probably end up with multi-component reaction and multi-component separation. Then the more than one reactor might be introduced inside the reactor. Probably a series of the separators should be involved in multi-component separation. This is a very simplified one, okay? So in a complex industrial scale process, no single reactor may be enough, no single separator is enough, no single heater coolers are enough. We may need to have the multiple heater, cooler, compressor, separator, reactor. So multi-stage operation is quite common in order to increase the performance of the process or to increase the separation performance or to decrease the energy consumption, okay? So let's say we have the A process. So this schematic diagram is called the flow sheet, okay? So we can see that the flow of the material stream and the energy stream is in a schematic way. So this diagram is called flow sheet. Then this heater, reactor, and cooler and separator, these things are called unit operation, okay? So device, or you may call it single equipment, that are categorized as under the name of the unit operation. I want to simulate it. I want to check how much product B is produced. I want to check how much unconverted A is recycled back to the reactor. Then I can check how many feed is required. I want to check how much B is produced through the reactor. I want to see how much steam is required in the heater. I want to see how much cooling water is required for this cooler, okay? And also I want to see how much energy should I provide for compression and the pump. Then I want to check the performance. Eventually the cost, how much profit I get by selling this product, how much energy is consumed, how much the feed material is used. So I want to check the profit against the cost. Then I needed to see how this process is working and the performance of the individual unit as well as performance of the overall process. So then we needed to set up the model first for each of the unit operation. So I needed to set up the model for the reactor. I needed to set up the model for compressor. I needed to set up for the heat exchanger. Then individual models are set up. Then I needed to link and combine together, okay? And they model the overall process, the whole flow sheet. Then somehow I needed to use numerical technique or using some computer simulator for this flow sheet. Then try to simulate the performance and of this process, and evaluate the design, the economics of design, sustainability of design, environmental performance of design, safety of the design, and so on. So we needed to check the flow sheet by setting up the individual module, then combine all these things together, then simulate, probably typically using the numerical technique, then simulate all the process in one single framework. So we are going to look at the one by one, so segment by segment. So here we have the feed, then this is a mixing junction. So in the feed, we have to specify. In other words, we have to give numbers. For example, flow rate and the composition and temperature and the pressure. So typically for the purpose of the process design, feed conditions are given, okay? So we typically say we want to produce B product based on the A, then we want to produce the X amount of the product B, let's say 1 million ton per day. Then based on the target productivity of the target product B, I can estimate how much feed is required, what is the reasonable composition for the feed, okay? When we specify these things, we need to check cost to purchase this feed. Also, I try to say availability, okay? So whether the market can afford the supply of this feed. If that is not enough, then we needed to have the upstream to produce A, okay? So when we have the upstream, we have the certain conditions that is given by the upstream. By the upstream, then specify the flow rate, composition, temperature, and the pressure. So once that is given, then the remaining, the mixing junction, is the simple mass and energy balance. So whatever happened down there, let's say we have the certain flow rate, certain composition, certain temperature, and the pressure, then mixed with the feed. Then that condition will be specified by the material balance and the energy balance, okay? So based on mass and energy balance, the mixing junction is not going to be difficult part, okay? But the question is, how can we know that condition for getting this point of the interest? So we get this number for composition, flow rate, temperature, pressure once we complete all the design for the separator. Otherwise, we cannot have that condition, okay? So in the beginning, we can take this one as 0, then continue the design without taking any flow rate coming from the separator for the time being. Then proceed the design and heater, followed by reactor, followed by cooler, followed by separator. Then we can see that how much A can be recycled. Then reflect actual recycled flow rate and composition from the separator, followed by compressor. Then apply the material and energy balance. So then this condition, previous case, is not going to be the same, because in the first case, we take this one as 0. But now we have the certain the magnitude for the flow rate, composition, and the operating condition. So we probably have a different number here. So what I'm saying here is we need to have some iterations in order to have converged solutions, okay? So if we have this recycle stream, iteration is inevitable, okay? A few steps of the iteration are required to have the converged the material balance and energy balance throughout the whole process, okay? In the beginning, you might assume certain number, or you might take an 0, but that's up to you. But you have to do certain the degree of the iterations, okay? If you don't want to do that, then if you don't want to do that iteration, then you set up the model, all the model for the unit operation. You need to set up the model for the mixing junction. Then, like we have done in the working session 4.1, we set up the aid equations, then solve all the aid equation simultaneously. So that is the second method. We set up all the equation like we have done in working session 4.1, then solve all equations simultaneously. Then we can have the model and simulate the performance. And first method is iteration. Assume certain number, calculate heater, calculate reactor, cooler, then define the separator, apply the compression, update it, repeat, update it, and repeat until we have a converged solution. That is first technique based on the iteration. Second technique, we set up all the mathematical equation. Then all the equation put into the one single, okay, all the equation into the one single mathematical framework, then solve them simultaneously at the same time. So that is the second way of solving the problem, okay? We have the heater, we have the cooler. So the temperature is given as TC1 and TC2. Here, cooler is given as TH1 and TH2. Only process stream is given for this expression. That is TH1, that is TH2, okay? So that stream, TC1 to TC2, is that stream, TC1, TC2. In this expression, this arrow and that arrow, blue arrow and red arrow, has not been expressed. Actually, this arrow is going to be like that, okay? And this one, this blue one, is going to be like that, okay? So that arrow, this one, and that one, has not been expressed. We just express in terms of the process stream. That one and that one is process stream. This one is supplied by steam or cooling water. That is called utility stream. This is a process stream. This arrow is utility stream. So utility stream has not been expressed in this the diagram on the T and the Q. But what happened actually in the heater and the cooler is to use another utility stream to remove heat or provide heat. Okay, but in terms of the simulation, we just concern about the amount of the Q required by the utility stream, and here amount of the Q to be removed by cooling water. So if I want to just know the amount of the steam from this process, what I needed to know is to just calculate this one, MCP dt. If I want to know the cooling water flow rate requirement from this cooler, what I just needed to find out is to get the Q from that equation, MCP dt. Okay, so cooling water and the steam has not been expressed in the equation. We just estimate based on the process stream for the cooler, process stream for the heater, in order to estimate Q for the steam, Q for the cooling water. Okay, so that is a simple way about the simulation of the heater and cooler. Why do we do these things? In the beginning, in the early stage of the process design, we do not know how we can provide the heating and the cooling for the process. We don't know how much steam is available. We don't know what the temperature would be for the cooling water in some case. We don't know whether we can produce the steam at the 200 degrees C. It's not clear at some point until final design is done. So in that case, we leave the decision for the heater, cooler later. So we just concern about the amount of the cooling requirement, amount of the heating requirement. Then later, at the final stage of design, we can confirm how we can provide the utility streams for the steam and the cooling water. Okay? So we don't need to specify heating or cooling medium. Then we just specify based on the energy balance for the process stream and define the number, define the duty for the Q. Okay, so steam may not be available. Then I'm using some other flue gas directly rather using steam. The cooling water may not be enough. Then I may use air. So that kind of decision can be made later stage. So we don't need to specify in the beginning of the process design how utility stream is provided. In that case, we can just calculate the heating duty or cooling duty. Okay. Of course, we can specify the temperature of the hot stream and temperature of the cold stream and try to simulate between these two streams. For this case, we have the process stream for hot stream and process stream for cold stream. Then we have to specify the temperature for inlet and the outlet and temperature of the cold side for inlet and the outlet. In that case, we can simulate based on the amount of heat exchange between the hot stream and the cold stream. So that is the amount of Q exchange based on that hot stream. Okay. The blue one, the heat should be added in order to increase the temperature from TC1 to TC2. That is given by that. Okay. That is given by this one. Okay. So this is based on the stream by stream calculation. So amount of Q is going to be the same as the amount of Q from the cold stream. Okay. So this expression MCPDT is based on the single stream, the temperature change. But if you're looking at this one, we can determine another way of the expression for heat exchanger. That will be, as we have seen in the previous lectures, Q equal UA log mean temperature. So that is the definition of log mean temperature. So that one and that one is given by that. Okay. Let's say A, that is A element. The difference here is B element, that is B. So the log mean temperature is given by A minus B ln A over B. So that is the log mean temperature difference. So using Q equal to UA log mean temperature, we have another expression. That Q is the same with this Q. It's not different, but the way expressed the Q is different. This one is based on the interaction between this red one against this blue one. Okay, so we have the three equations. So based on this expression, we can estimate size required for this heat exchanger. Then how can we ensure the heat exchanger required by this heat exchange based on this amount of Q? That is called the design. We needed to provide number of the tube here and the big size of the shell to allow heat exchange between this cold stream and this hot stream through the design. Design means for heat exchanger, for example, we needed to decide how many tubes should be installed inside this heat exchanger, length of the tube, and the size of the shell. Okay, so this is by the way, this is one of the common heat exchanger used in the process industry that is widely called as shell and tube heat exchanger. You can see that the horizontal tube, and along the horizontal tube in our circuit we have the big shell, the tank, okay, horizontal tank. Then the one fluid comes into that direction. In this case, that is cold stream. Then going through this pipe. Then the fluid is accumulated at the other end. Then cold fluid is removed from this side. But then through the heat exchange, the temperature is increased. Okay. The one fluid goes through the inside the tube. the other fluid goes through outside the tube. Okay, so that is emphasized with this so-called shell arrangement. So this horizontal drum allows the movement of the hot fluid. So the fluid come in, then the up and down along the tube. So heat is exchanged from this cold stream and hot stream. And that hot stream coming down from this point. Then this one is called the buffer in order to have the upside down movement. So based on the choice of the number of the tubes and diameter of the tube, and if you're looking at that side, you might put that this tube in a rectangular position, or you might want to place as this triangle position. So based on the configuration of the arrangement of the tube, then the amount of Q is different. Okay, so in other words, if I want to ensure the amount of Q by that the design, I need to introduce enough A, the heat exchange area for this heat transfer. What is the heat transfer area? So number of tubes, out circuit of the number of tubes, that will be the out surface of the tubes will be the heat exchange area. Okay, because through that surface we have the exchange between hot fluid and the cold fluid. How many? How big? That will determine number of the tube and the size of the shell. That will determine the heat exchange area. Based on the choice of your design, you can see whether you can achieve the amount of Q exchange between hot and cold stream. Okay. Here, UA may be lumped. So actually the overheat transfer coefficient is function of the temperature and the flow rate and the physical property and also geometry of this heat exchanger. So that is very complex business to estimate the overheat transfer coefficient. So the overheat transfer coefficient might be specified or maybe assumed. Okay. Then it may not be easy in the beginning. So UA may be lumped and assumed as a one single number. Then once we have more understanding on this process, then we can elaborate how A can be specified based on design. Then we can see more clearly how we can define the U, or how we can estimate U. Okay. So how do you get this kind of information for the U? From database or the journal or some books. Then you can find the information for the guideline, how we can set the initial estimation of the overheat transfer coefficient. Okay. Once we have the U, then we can calculate the A. Okay. So next one is the reactor. The reactor should be simulated based on the model you decide to use. So simplest one is conversion reactor. What is conversion reactor? So we have the reactor. So simplest one is based on the conversion. So say a 90%, maybe 70% of conversion. And I have, okay, amount of the A left after X% of the conversion. Okay. So if A turned to B, then the B will be C, B will be CA0X. Okay. So based on the conversion, then we have the some indication how much A will be produced, how much B will be produced, how much A is reduced after the reaction. Okay. So conversion is the simplest way of the simulating the process. So what is second one? So the equilibrium and the kinetic one. Let's say let's say this reaction is based on KCA. So first order reaction, then the Arrhenius constant K will be used as a reaction constant. So these reactions follow the first order behavior as a kinetics. Then using the kinetics, we can have the volume of the reactor, we can have the concentration of the reactor. Okay? So this is so-called the estimation of the performance of reactor based on reactor kinetics. Okay? What about the second one, equilibrium reactor? So let's say so tetroxide N2O4 is decomposed into the nitrogen dioxide NO2. So this is a very common, typical example of the equilibrium reactor. So A turn to B. So what is the let's say the equilibrium the reaction? So that is typically expressed with a K constant, right? So then that may be expressed with Ca and Cbe square. Okay, so this is another way of expressing the equilibrium reactor. So this is based on the kinetic reactor. Whatever happened, then we can correlate this information to the conversion and the reactor volume and the stoichiometric of the concentration chain. Okay, so this is the simplest one. This is a little bit complex, but based on the kinetics, then we can correlate the stoichiometric and the reactor sizing and the conversion. So with either using equilibrium reactor or the equilibrium reaction, or the non-equilibrium reaction, we can use kinetic information. Then we have that expression. Okay, so that is called the reaction design. Okay, once we have the relationship with that, then we can go further to determine the temperature dependence and the pressure dependence for the reaction. Okay, so some reaction is heavily dependent on the temperature, choice of temperature and the pressure, especially for the equilibrium reaction. Okay, then do you remember the Louis-Chatelet principle? Louis-Chatelet principle. So based on choice of temperature for the exothermic reaction, it might be better to decrease the temperature. For the endothermic reaction, it's better to increase the temperature in order to have the high conversion or high equilibrium conversion in the reaction. So temperature and the pressure dependence will be explored further. So this is called the reactor design. Okay, the reactor design. Then, in order to have this relationship, we need to define either conversion, either the reaction kinetics, or the equilibrium information. Okay, so based on this, the reactor model, we can check how much B is produced, how much A is remain after the reactor. Okay. By the way, I'm not going to teach how to simulate reactor in detail, how to estimate the size, how to calculate the stoichiometric of the reactor. I'm not going to teach how to determine the conversion, correlate with the volume of the stoichiometry. So these subjects are related with reaction engineering. So you need to look at more detail, how to simulate these things, how to set up these equations from the reaction engineering books. What I'm saying is this is important for the simulation purpose. Then, if the X is not enough, then we needed to look at the multi-stage operation. okay, like a three-stage PFR reaction, maybe CSTR followed by the PFR. So you can go further beyond the single reactor to multi-stage reaction, okay? So that should be explored. So cooler is required here, then this before the separator. So next one is to how to simulate the separator, okay? So many possibility for the separation as long as we have the certain the component to be separated by separator. Then we have to check the functionality of the separator and then the match, the most economic or the best performance separator for having the particular separation task. So here we need to separate A and B. The simple splitter is given. The splitter is used in a more like modeling purpose. In real world, in real engineering world, we don't have a splitter, okay? The simple splitter means, let's say we have the A and B, then we have the 90% of the A in the top and the 10% of the A in the bottom. We just assume like conversion in the reactor, we can use recovery just to fix this number. Then arbitrary, not the arbitrary, sorry. We choose the recovery, then use that number. So this is a very simplified reaction performance, but that is for the sake of the simulation, but this is not happening in real world. We needed to use some flash or distillation, absorption, extraction, or some other things. So we have the A and B. Then we needed to separate it. Okay? So A and B. How can you separate? How can you separate? We need to check the, as I explained in the lecture 3, we need to check the physical properties. We have to check physical property. Why? So let's say if the density of the A is significantly different with the density of B, then we can have the settling. We just put that in the tank. Then A will be separated with B, okay, through the phase separation. That's probably easy. So if you have the big diameter, heavy one, you have the small one. How can I separate this? I may using the blowing of this component, then the heavy one will be dropped down quickly and small one move further, so that will be accumulated here, bigger one accumulated here. When I blowing with pan, okay, that is the one of way based on the physical property difference, okay. Then if this is a simple operation is not working, what should I do? I need to check the thermodynamic property or relationship. Thermodynamic property or thermodynamic relationship. For example, if I want to use distillation column, I need to check the volatility. So if the volatility of the A, B is significantly different, I can use alpha, A and B is big, then I can use the distillations. I explained in lecture 3, okay, when I was using the importance of thermodynamic using the distillation column. I explained such that the separation is occur based on the relative difference in the volatility. A is light, B is heavy. Then A is likely to evaporate, B is likely to condense. Then we can use distillation for the separation between A and B. How do you check this volatility? That is based on the vapor-liquid equilibrium. Vapor-liquid equilibrium based on the thermodynamic property. Okay, if AB is close to 1, we cannot use distillation. Then I'm checking another one. Say, do you remember the Henry constant? What is the meaning of Henry constant? Henry constant is the constant for reflecting the capacity of the absorbing the gas to the liquid, okay? So if the solubility of the gas to the solvent is different, so solubility A against B is different, then we used, for the gas, we use the absorption. Okay? So if the solubility is not close enough, then we cannot use the absorption. Then we need to check another thermodynamic property. What else? We may use the liquid solubility. So we have the A and we have the B that mixed with the C. So A is mixed well with the C, B is not mixed well with B. Then we may have this phase separation. Then we can take out A from B by adding external component of C. So this kind of the separation is called extraction. So what I'm saying here is, based on the physical property and the thermodynamic property, we needed to find separator and match for this separation task. So there are many possibilities. Okay, in the reactor you have a CSTR, PFR, okay, and the batch reactor you don't have a large number of different reactor type. But for the separator, we have a large number of possibility, because we need to check the physical property and thermodynamic property based on the choice of your interest. Then we can apply these separations. So unfortunately, we needed to work out with a large number of the options, then find the best one. Sorry. And the other thing should be remembered is that the separation in a chemical process is not the binary situation. It's multi-component separation. For example, you're not going to have the separation A and B. You probably have A, B, C, D, E. Then you have to separate A and B and C, maybe D, E together. Okay? You're not going to have the single separation. You have the multiple separation, okay? So in that case, you have the series of the separator, okay? In order to have the A and B and C, blah, blah, blah. So you have the multiple train of the separator. That is quite common in the process industry. But I'm not going to discuss how to determine the sequence of the separator for the time being. Then I'll leave it for the later, okay? So, but at this stage, you need to remember the number of the separators are required to separate multi-component separation. Then, unfortunately, we have many possibilities of the option for the separator. So, in conclusion, it's very complex for the design the separator system. In this case, we used a very simple the method like conversion, the recovery, but for the distillation, absorption, or extraction, or other things, or membrane, whatever, we may not be able to use very simple the indicator. In that case, it's modeling is very complex. Once we have the separator, then we need to store the product here to the downstream process. Then we need some transportation. So the liquid is produced from this separator. Then we needed to install the pump. What is the main thing we want to know from the design of the pump? The main thing is how much energy is required by this pump. Then second thing is what is the size for the pump. Okay, so that is size is mainly related by flow rate. Okay, and also the size is related by pressure drop, because how much pressure should be increased through that pump, that will be influencing for determining size of the pump. And also we want to see how much energy is required by that pump. Again, that is governed by flow rate and the pressure drop. So this is a very simplified equation. So power required by this pump is typically given by flow rate multiplied with the pressure drop, pressure increase through the pump, and divided by the efficiency. Okay. So we have the pipe, then we have the pump, we have the transfer from position A to B. Okay, so we have the let's say kilometer. Okay, then the pumping required by this process, the pipe and the pump is, let's say, 100 tons per hour. Okay, then let's say, okay, so 1000 tons per hour. Then you can calculate the size of the pump and the power required by the pump based on this flow rate. But then how do we calculate the size and the power required by this process? So it depends on your piping. Say somebody may say, I have the one single pipe. Okay, I may split it, have the two small pipe. Okay, then you have different flow rate and different velocity. So you have a different pressure drop. Okay, so pressure drop is different. Okay, then are you going to use the one single pump? Are you going to use the two pump? Based on that, you have the different size and different pumping requirement. Okay, so it's not just a simple calculation from the viewpoint of pump that is connected with design of the pipe. Shall I make the big diameter or smaller diameter? If you have a big diameter, then the piping is expensive, but then the pressure drop is going to be decreased because you have the large diameter. If you have the small size, the pipe, then your piping cost is to be decreased, but pressure drop is increased because you have the smaller diameter. As long as we have the same flow rate, so that is some trade-off. And this is based on the one single pipe. But you might say, I want to do two small pipe rather than one big pipe. Then you have different story. So the pump size, and the pumping power requirement is governed by the piping network design and choice of the diameter for the pipe. Okay. The next one is the design of the compressor. Okay, so the A stream is recycled back to the reactor. Then if the A is produced as a gas phase, then we have to use compressor. So the pressure comes in, feed comes into the compressor at the pressure of the P in, then use the external power, then the pressure is increased. So that device is opposite device of the turbine. So this device is called a compressor. Okay. Then we have seen the steam turbine in the lecture 2. So in a steam turbine, we have the P in and P out. Now we have the same diagram, enthalpy and the entropy. Here is a P1 and P2. So it's dropping down. The actual one is go to that way. So that deviation is reflected with the efficiency. Okay. Here it's opposite. We needed to increase the pressure. Okay. We needed to increase the pressure. So pressure is to be increased. So at the P out, at the ideal isentropy compression, we have that situation, that point. But the compression is not ideal. We have the actual compression outlet condition here. So real compression require more power than isentropic compression. Okay. So starting point here, the compression path does not based on the isentropic compression. So that goes to real expansion path. So that will be reflected by efficiency. Okay. So that is the same mechanism when we have the estimation of the power. Okay. So from that equations, the enthalpy difference will be estimated with the isentropic difference of the enthalpy. That will be reflected by the efficiency, thermodynamic efficiency. Okay, so that is called the isentropic compressor efficiency. We have the another efficiency. Okay, that is related with mechanical efficiency. So in a thermodynamic point of view, real compression is not the same with the isentropic compression. So some degree of the non-ideality is reflected with this efficiency based on isentropic efficiency. This is a purely thermodynamic deviation from the ideal situation. Okay, the mechanical efficiency is related with any loss related with the device. Okay, not based on the thermodynamic device itself. Mechanically, the sum of the power is not transferred fully to the compression of the gas. That is reflected by compressor mechanical efficiency. The typically mechanical efficiency is almost close to 1, say. So sometimes mechanical efficiency is not considered. However, it's not actually 1, 99% or 98.5%. So people sometimes neglect mechanical efficiency, but the main deviation comes from the thermodynamic inefficiency. So we typically use the isentropic compressive efficiency, but strictly speaking, we needed to consider mechanical efficiency for the compressor. So once we have it, then we need to consider piping and the hydraulics. And here, the feed brought in probably through the pipe. Okay, between the reactor and the separator, we probably have the pipe. Between the separator and the heater, we probably have the pipe. Then in the pipe, we have some pressure drop, and also the reactor, heat exchanger, cooler, separator. All the unit operation had a certain degree of pressure drop. Okay, so we have to consider the piping, pressure drop, and its hydraulics in the chemical process design. So the fluid flowing through the pipe and vessel typically have the pressure drop. So this, in the beginning, typically ignored, but it should be taken into account. Otherwise, we may not have the proper operation in a chemical process. Also, the sizing pump and the compressor, the delta P, the pressure drop is important. So we need to check the power consumption here and the power requirement by pump. Then we needed to check the size and the size, but that is related by the pressure increase here and the pressure increase here. So in terms of the finding out the pump sizing and the compressor sizing, we have to check the pressure drop. So how do you know that the pressure increase from here to here? That is related with the pressure drop from heater, reactor, cooler, and the separator. Because we needed to recover the pressure in order to be processed by the reactor. What about the pump? We need some downstream process here. Now, probably that is storage. Now we have to transfer from here to the final storage tank. Then there may be some distance. Then the pipe, the pressure drop loss. Based on this, we can estimate the size of the pump. Okay, so pressure drop is the essential for estimating size of the pump and the compressor. Then we need a good model, consider layout of a plant and the piping. So for example, here is the place of the A, here is the place of the B. It may be up and down, and we may have some bending in order to have transportation of the from A to B. Then when you have this bending, when you have this height difference, the pressure drop is going to be increased. So when you have this the valve or some device for the control purpose, for like a sensor, then the pressure drop is going to increase. So we need to take into account not only the distance and also the change in height and the number of bend, number of valve, etc. Then we need to check the component for determining pressure drop. Okay, so we need to have some information for plant layout in order to have the correct estimation, accurate estimation of pressure drop in the process. So in this lecture, we discussed how we can simulate the overall process. The first step is to set up the unit operation model individually. Then we needed to connect them and then simulate them all together in a single mathematical modeling environment. So then once we have the model, then we can check the performance of the flow sheet. So you may have different options. You may have different operating conditions. Based on the model, you are able to check the impact of change in your design option or change in your operating condition. So the simple and straightforward the modeling method is to use the material and energy balance. These are the most important equation for simulating unit operation in chemical process design. So models can be overspecified, underspecified. So we need to check the number of equations against the number of variables. If number of equations are not enough, then we needed to specify some of the parameter or design variable in order to have the process simulation. Many different options are available in the process. So the typical tactic in engineering world is to use the commercial simulation software. Otherwise, we needed to simplify the performance of the model, then simulate it, the whole process. Okay. Then otherwise you needed to define all the equation for your simulation, then solve those equations all together, for example, by using the programming, okay? So manual calculation is limited. There are certain things we can do through the manual calculation, but the chemical process design is very complex. Because of the large number of components involved in, large number of equations are interacted together. Also, more than one unit are involved in the separator and the reactor. So with a certain support of the automated the simulation software will be inevitable. Okay, so it is logical to use commercial simulation software for large size problem. Okay, so if you're working in an industry later, so in a petrochemical company or engineering company, it is quite common to use the simulation software. You can set up the modeling in an Excel environment, but it is limited because lacks of the numerical the method availability for simulation. So in a complex simulation, especially when the thermodynamics are involved in your calculation, it's very complex to be solved through the manual method. So the simulation software is widely used in the process industry. So I'm recommending you in future to learn, if you have a chance, then to learn the commercial simulation software. Okay.